There are two versions of the M272V configuration engine on the market, a port injection version and a direct injection version. In this program, we'll refer to the port injection version as the KE engine and the direct injection version as the DE engine. This program will focus on the special features of the DE version. Chapter 1 looks at some of the basic features which distinguish the DE version from the KE version. These include the mechanical engine systems, the control unit, a new bus, and the coolant circuits. Let's begin with the shape of the pistons. On the KE, the piston crown is flat. By comparison, the piston crown on the DE has been raised by the addition of ring-shaped material. The additional material makes the combustion chamber smaller and consequently increases compression. The layout of the components in the cylinder head is also different. On the KE engine, the spark plug is positioned centrally in the cylinder, whilst the injector is on the side. On the DE engine, the center position is occupied by the injector. This benefits the new spray-guided combustion process. The spark plug has been moved to the exhaust side and is installed at an angle so that the spark plug's overhead electrode is immersed precisely into the edge of the injection spray cone. Now let's have a look at the engine electronics control unit. On the DE engine, it is exposed to higher levels of heat. The output stages of the piezo fuel injectors incorporated into the control unit, for example, generate an operating voltage of up to 160 volts. To dissipate the heat, the ME control unit is therefore liquid-cooled. On the DE engine, the control unit must also actuate a number of additional components. These are the actuator motors for external exhaust gas recirculation, the shut-off valve for the low-temperature cooling system, the pressure regulating valve, and the quantity control valve of the fuel system's high-pressure circuit. The DE engine has an additional sensor data bus, CAN-S, which is controlled by the ME control unit. Also using the bus, in addition to the ME and fuel pump control units, are the two nitrogen oxide sensors with integral control units. The sensors are required for stratified-charge operation. The additional CAN-S bus only links these 4 bus users and, amongst other things, permits diagnosis of the fuel pump control unit. The cooling system on the DE is somewhat more complex than on the KE. Let's start with the conventional coolant circuit, as found on the KE engine. The heated coolant flows from the engine to the radiator, where it is cooled. The coolant is pumped back to the engine by the coolant pump. The triple-plate thermostat ensures precise heat management. Depending on requirements, the heating system can be connected to or disconnected from the coolant circuit via a shut-off valve. The DE engine variant has 2 additional coolant circuits. Both can be connected and disconnected by means of a common shut-off valve. Let's look first at the coolant circuit for external exhaust gas recirculation. Its task is to cool some of the components that are particularly sensitive to heat. These are the 2 actuator motors for regulating the amount of recirculated exhaust gas, and the connecting pipe through which the recirculated exhaust gases flow back to the intake pipe. The DE engine also has another circuit, the low-temperature coolant circuit. This helps to reduce the coolant temperature even further by means of a second radiator. The low-temperature coolant circuit is used to cool the engine control unit and the fuel. The shut-off valve, shared by the two additional coolant circuits, is map-controlled. The critical parameters are the fuel temperature, the temperature of the engine control unit, and the exhaust gas recirculation rate. Direct injection engines essentially have two different modes: homogeneous mode and stratified charge mode. The same goes for the M272DE. This chapter looks at the differences between homogeneous and stratified charge modes and some of the special features of the combustion process and air ducting. But why have two different operating modes anyway? It's all a question of priority, and to this question, there is a clear answer. In homogeneous mode, the priority is high torque and high power output. By contrast, in stratified charge mode, the priority is to minimize fuel consumption. The engine control unit switches between these two operating modes according to requirements, without impairing driving performance. The switching is map-controlled, using a number of parameters. Playing an important role here, alongside such parameters as engine load and engine speed, is the operating status of the nitrogen oxide catalysts. In general, we can say that the engine runs in homogeneous mode when idling and at full load. In the part load range, however, it operates primarily in stratified charge mode to reduce fuel consumption. Here, the most crucial limiting factor to be taken into account is the status of the NOx catalysts. Here's a brief overview of the main functional differences between homogeneous operation and stratified charge operation. By the way, a more detailed analysis of these differences can be found in the study program Direct-Injection Petrol Engines. In homogeneous mode, the engine is operated approximately at lambda equals 1. The mixture ratio is uniform throughout the entire combustion chamber. The mixture cloud is therefore homogeneous. By contrast, in stratified charge mode, the mixture ratios in the injection spray cone range from lambda equals 1 to an extremely lean lambda equals 3. The mixture cloud is therefore non-homogeneous or stratified, hence the name of this operating mode. Ignitability is ensured by targeted injection at the spark plug's overhead electrode. The result is an average lambda value of between 1.3 and 2.5 for the combustion chamber as a whole. In homogeneous mode, internal exhaust gas recirculation by means of valve overlap is sufficient. External recirculation is deactivated. In stratified charge mode, both internal and external exhaust gas recirculation are deployed. The recirculation rate can be as much as 30%. In homogeneous mode, injection takes place during the intake stroke, as is usual in petrol engines. In stratified charge mode, however, injection takes place during the compression stroke instead. Homogeneous mode and stratified charge mode differ greatly when it comes to exhaust gas treatment. In homogeneous mode, the oxides of nitrogen are converted, along with the other pollutants, in the three-way catalysts as normal. In stratified charge mode, it is not possible to catalyze the oxides of nitrogen because of the very lean mixture. The three-way catalysts are ineffective here. As a result, the unconverted oxides of nitrogen are first stored in special NOx storage catalysts. However, these stores only have limited absorption capacity. They have to be continually regenerated. To regenerate them, the engine is switched briefly to homogeneous mode. Once the lambda value is less than 1, the stored oxides of nitrogen can be converted as normal. Let's now have a closer look at stratified charge mode. This operating mode uses a completely new type of combustion process, known as the spray-guided combustion process. Here, the shape of the spray is determined purely by the injection nozzle. Specially developed piezo injectors are used as the injection nozzles. The spray-guided combustion process is necessary for stratified-charge mode, but also ensures excellent combustion in homogeneous mode. The mixture cloud created by the spray has a hollow cone shape and is located in the center of the combustion chamber. The mixture composition in the cone-shaped cloud is stratified. The lambda value varies between around 1 at the cone wall and around 3 in the center of the cone. The mixture, therefore, gets leaner towards the center of the cone. Outside the conical cloud is a layer of air that is virtually free of fuel. In other words, the lambda value outside the spray cone is very high, virtually infinite. Strictly speaking, this is an air exhaust gas mixture, since external exhaust gas recirculation is activated in stratified charge mode. This air exhaust gas layer insulates the flame from the cylinder wall, thereby stabilizing the combustion temperature. The average lambda value for the combustion chamber as a whole is between 1.3 and 2.5. A lean mixture like this ensures complete combustion. This reduces fuel consumption and consequently pollutant emissions substantially. Maximum ignitability is ensured by the fact that the wall of the conical cloud, where lambda is around 1, lies directly in the path of the spark from the spark plug. With the spray-guided combustion process, therefore, it is important that the spark plug is positioned exactly. The overhead electrode must have a precisely defined position with respect to the conical spray. If the spark plug is slightly too high, the path of the spark will be outside the spray cone. The ignition spark will not come into contact with the mixture at all. If the spark plug is too low, it will protrude into the lean layers of the spray cone. Likewise, here too, there is no guarantee that ignition will occur. As a result, it is particularly vital that the tightening torque for the spark plugs of the DE engine is adhered to exactly. Depending on load, there are either 2 or 3 injection processes per ignition process in stratified charge mode. Pilot injection and main injection occur before ignition. The optional post-injection process occurs, if at all, after ignition. The previously mentioned piezo injectors are required in order to achieve these very short injection intervals. In stratified charge mode, the engine is essentially de-throttled. The injection quantity is therefore no longer determined by the mass of air being supplied. This ensures maximum supply of intake air under all operating conditions. External exhaust gas recirculation is also enabled in stratified charge mode. Feeding in exhaust gas with a low oxygen content lowers the combustion peak temperature and consequently also reduces the formation of nitrogen oxides. This means that the intervals between storage catalyst regeneration phases, the phases which require a switch to homogeneous mode, increase. Or, expressed another way, the duration of uninterrupted stratified charge mode is increased. In the air-ducting system of the DE engine, there are 2 particular features which distinguish it from that of the KE variant. Firstly, there are no tumble flaps. Secondly, the throttle valve actuator is only used in homogeneous mode to regulate intake air. In stratified charge mode, it is always fully open. The engine is therefore de-throttled. As you have already seen, external exhaust gas recirculation is activated in stratified charge mode. For this, the DE engine requires some special components. The exhaust gas is removed from behind the 2 three-way catalysts. It is first conveyed towards the intake pipe in two separate lines. The recirculation rate can be steplessly regulated. Specifically, up to 30% of the intake air quantity can be made up of exhaust gas. The ME control unit regulates the recirculation rate in accordance with a map and as a function of engine load. Each of the two recirculation lines has a continuously variable valve with actuator motor. The valves and motors are combined into one single compact component. Behind the recirculation valves, the exhaust gases are combined into one single connecting pipe and conveyed into the intake pipe. And as you already know, both the actuator motors and the connecting pipe are liquid-cooled. As you saw earlier, the spark plug on the DE engine, unlike on the KE engine, is not positioned centrally above the cylinder. It is now located on the exhaust side. This also means that the ignition coil has had to move. Instead of being connected directly to the spark plug, it is positioned above it and connected to it by means of a cable. The following chapter deals with the special features of the fuel system on the DE variant of the M272 engine. Let's concentrate first on the low-pressure side of the fuel circuit. How does it differ from the circuit on the port injection variant? On the direct injection engine, the fuel pressure on the low-pressure side is not controlled by a pressure-regulating valve, but is instead recorded by a special sensor. Specifically, the fuel pressure sensor located in the feed line downstream of the filter. The signal from the fuel pressure sensor is recorded by the fuel pump control unit. The pressure readings are sent via the sensor data bus to the ME control unit. The ME control unit checks the current fuel pressure against a map and forwards the recalculated pressure specifications to the fuel pump control unit. The fuel pump control unit regulates the rotational speed and thereby the pump delivery rate via a PWM signal until the required fuel pressure is achieved. Low fuel pressure is regulated between approximately 3.0 and 5.5 bar, depending on engine operating status and fuel temperature. The fuel supplied by the low-pressure pump and the return line from the high-pressure side converge at the low-pressure fuel supply rail. The fuel is forwarded from the low-pressure fuel supply rail to the high-pressure pump. Fuel temperature at the inlet to the high-pressure pump may not exceed around 70 degrees centigrade. The temperature is monitored by the ME control unit with the aid of the fuel temperature sensor. This is incorporated into the low-pressure fuel supply rail. A fuel cooler is incorporated into the return line to lower the fuel temperature. Spray-guided direct injection requires a high fuel pressure of up to 200 bar. The high-pressure pump delivers fuel at the appropriate pressure to both rails via the high-pressure fuel supply rail. By the way, the stainless steel high-pressure lines must not be reused once they have been removed because the tightness of the joints can no longer be guaranteed. The pressure is stored in the rails. The rail pressure sensor continually informs the ME control unit about the current pressure in the rails. The control unit regulates the rail pressure by means of two actuators, namely the quantity control valve, which is incorporated into the high-pressure pump, and the pressure regulating valve. This is mounted on the high-pressure fuel supply rail. Both valves are controlled with PWM signals. The quantity control valve is closed when a continuous current is applied, in other words, when the pulse duty factor is 100%. With the pressure regulating valve, it's exactly the opposite. It closes if no current is applied, in other words, when the pulse duty factor is 0. Which of the two valves plays the main role in regulating the high fuel pressure depends on the engine's operating status. The high-pressure starting operating status prevails up to approximately 5 seconds after engine start. In high-pressure starting conditions, the quantity control valve is closed by applying a continuous current. The high-pressure pump can therefore supply fuel at the full delivery rate, which enables pressure to be built up quickly. In high-pressure starting conditions, the rail pressure is regulated exclusively by the pressure-regulating valve. During a high-pressure start, the low fuel pressure is regulated to between 5 and 5.5 bar. Normal operation refers to fault-free driving mode and applies to all load ranges. In normal operating mode, the pressure-regulating valve is de-energized and therefore closed. In normal operating mode, rail pressure is regulated exclusively by means of the quantity control valve. The low fuel pressure is regulated to between 3 and 5.5 bar in normal mode. The control parameter for low pressure is the fuel temperature. The aim is to prevent bubble formation. In the switching off operating state, the pressure-regulating valve and the quantity control valve are operated for a further 60 seconds, or so to release the pressure via the return line. During this period, no current is applied to the quantity control valve. In other words, the valve is open. By contrast, the pressure-regulating valve is actuated with a pulse duty factor of approximately 70%. In other words, it is held approximately 70% open. The low-pressure fuel pump is not actuated during the switch-off procedure. If certain problems occur with the high-pressure circuit, the system is switched to the low-pressure emergency operating mode. The quantity control valve is open in this operating state. Because this means that the maximum amount of fuel is diverted, it is no longer possible to generate a high pressure. The pressure-regulating valve is held open with a pulse duty factor of approximately 70%. This means that the rails are only supplied with fuel from the low-pressure fuel pump, in other words, at a pressure of 5 to 5.5 bar. The low rail pressure is compensated for by actuating the injectors for a longer period. The stratified-charge mode is not permitted during low-pressure emergency operation. Engine power is reduced to the extent that it's only possible to achieve a top speed of 70 km per hour. A special fuel injector has been developed to handle the extremely short injection intervals of stratified-charge mode on the DE engine. It utilizes the piezoelectric principle. Let's have a look at this in detail. The nozzle module opens outwards. Thanks to its geometry, it is able to form a hollow conical spray which, in the spray-guided combustion process, must have a precisely defined shape and must maintain that shape for all operating conditions. Lengthwise, the actuator module is structured as a series of layers. This way, the expansion lengths of the individual piezo layers are added together for a cumulative effect. A coupler module is used to hold both the actuator module and the nozzle module free of play in the direction of expansion. This ensures that the entire longitudinal expansion of the piezo layers can act on the nozzle needle free of play. The fuel feed line supplies the injector with fuel at high pressures of up to 200 bar. The injector is actuated by the ME control unit via the electrical connections. The operating voltage is between 125 and 160 volts. The control current approximately 8 amperes. The exhaust systems of the KE and DE engines differ from each other considerably. This is firstly because oxides of nitrogen have to be treated in a special way on the DE engine due to how the engine operates. And secondly, because air injection has been dispensed with. The DE variant has adopted the conventional three-way catalytic converters with broadband lambda sensors in front and so-called voltage jump sensors behind from the port injection engine. However, because catalytic converters can only convert oxides of nitrogen in homogeneous mode and not in stratified charge mode, some additional components are also required. 2 NOx storage catalysts are used in addition to the conventional three-way catalysts. They work like normal catalysts, but are also able to store oxides of nitrogen. 2 NOx sensors, each one having an integral control unit, are located behind the storage catalysts and monitor the storage conditions. The optimum working range of the storage catalysts is between 250 and 500 degrees centigrade. Temperatures should, under no circumstances, exceed 800 degrees centigrade, otherwise the catalyst will be destroyed. As a result, 2 temperature sensors in front of the NOx storage catalysts are required. The exhaust gas temperature is correspondingly regulated by means of the exhaust gas composition. Let's have a look at how the NOx conversion control loop on the storage catalyst works. In stratified charge mode, in other words, when the mixture is lean with a lambda value considerably higher than 1, oxides of nitrogen cannot be converted. But of course, they can't simply be released into the environment. Thanks to a special coating, the storage catalyst is able to chemically bind the unconverted oxides of nitrogen. The catalyst is filled to the limits of its storage capacity with oxides of nitrogen. If an optimum driving style is adopted, this storage phase can last up to 20 minutes. Once there is no more storage capacity left, the oxides of nitrogen will start to pass through the NOx storage catalyst. In other words, the concentration of nitrogen oxides in the exhaust gas will start to rise. This will be detected by the NOx sensors. When this happens, the engine will be temporarily switched to homogeneous mode for a few seconds. In this mode, the mixture is made richer until lambda is around 0.8. This increases the amount of carbon monoxide present, which releases the oxides of nitrogen from their chemical binding and brings about their conversion into harmless products. Within a short period of time, the storage catalyst is regenerated. In other words, the NOx store is vacant again. The engine can now be switched back to stratified charge mode. The control cycle starts again from the beginning. By the way, the NOx storage catalyst is dealt with in even greater depth in the study program Direct-Injection Petrol Engines. On the port injection engine, secondary air is injected into the exhaust gas in order to heat the catalysts up quickly during the warm-up phase. On the DE engine, this secondary air injection has been dispensed with completely. Instead, the catalysts are heated up by adapting the air-fuel mixture in the engine. The mixture is temporarily made richer so that the fuel is not burned completely during the combustion stroke. The remaining fuel components are oxidized in the catalysts, which causes the catalyst to heat up quickly.